So we've learned how to do standard deviation of the mean, and confidence intervals in Excel. Okay, so let's look at how we can interpret those. If we were to repeat a measurement an infinite number of times, the standard, and you could calculate the standard deviation for that, what you get is called the population standard deviation, represented by the letter sigma. Okay, the mean of that infinite number of measurements would be called the population mean, Greek letter mu, and that would be equal to the true value, assuming all the errors are random and normally distributed. In other words, all the avoidable errors you've gotten rid of, okay, and the only remaining errors in all of those measurements are random errors. Those random errors are going to average out to 0. So you get the mean is going to be the true value. But your random errors are unavoidable, okay, so these errors will follow what's called a normal distribution or Gaussian distribution, okay, if they follow this expression right here. If the distribution of those errors follow this expression right here, then we say those random errors are normally distributed. Okay, so if x is a possible outcome of a measurement, and z is the random error, the difference between the outcome and the true value, what is z in terms of x and mu? Z would just be the outcome minus the true value, right? So the difference, so that's just the random error. Now, so if P of z, okay, P versus z is given by this expression, okay, and then we say those random errors. Did I start recording? Yeah, I did. So those random errors we say are normally distributed. So what would this graph look like? You remember from our lesson on Gaussian functions? A bell curve with a peak at z equals 0, right? And what is our FWHM? Do you remember? What's this maximum value right here? This is just 1 over sigma squared of 2 pi, right? And what was the generic expression for a Gaussian function? Y equals y max e to the minus 4 ln of 2 times 4 ln of 2 x minus x center squared over FWHM squared, right? So what is FWHM then? So you can see that minus 1 over 2 sigma squared is equal to minus 4 ln 2 FWHM squared. So what's our FWHM in terms of sigma? Negative cancels out, so that means 8 ln of 2. Okay, FWHM squared is 8 ln of 2 times sigma squared, so your FWHM is just square root of 8 ln of 2 times sigma, right? Now what is square root of 8 ln of 2? Let's bring up math again. So 8 times ln of 2, take the square root of that. Oops. Square root of that equals 2.35 sigma. Okay, so 2.36 sigma. So this width right here, do I have it right? Yeah. Okay. So this width right here is FWHM. So at half maximum, the width from here to here, this difference is 2.36 sigma. Okay? So if I were to give you a bell curve and I ask you, what's the standard deviation? What do? Find the half maximum, right? Find the maximum, take half of it, and then draw that for a horizontal line. Get the width at half maximum, the full width at half maximum. That's what FWHM means, right? And that's going to be equal to 2.36 times sigma. So you divide that by 2.36, that would tell you what sigma is. All right. So anyway, this is your Gaussian function, your normal distribution function. So P of z is called the probability density function. Okay, so the integral of P of z dz from A to B is the probability that you're going to get an error, a random error between z equals A and z equals B. Okay? So, in other words, probability that your error would be somewhere between A and B. Okay? So P of z is an example of a Gaussian function. What happens to P of z as z approaches positive or negative infinity? What happens when z approaches infinity or negative infinity? Yeah. So you can see your bell curve goes to 0 that way. As z approaches infinity, it goes to 0 as z equals negative infinity. So what types of random errors are more probable then? Larger errors or smaller errors? Smaller errors. So if errors are random, the smaller errors, the smaller values of z have a higher probability of happening. Okay. What's the integral of P of z from z equals negative sigma to z equals plus sigma? You did that in your Gaussian activity. What did you find? 68.3%, right? Let's do that in MathCAD. Okay, so I'm going to define z equals, let's just say, start from negative 5, negative 4.9, all the way to 5. Okay, and I'm going to define P of z equals, what was the formula? 1 over sigma times square root of 2 times pi times e raised to the power, what? Minus z over 2 times sigma squared, z squared. Alright, so MathCAD's complaining that it doesn't know what sigma is. So let's just define sigma to be 1. Okay? So if I were to plot this, what would I get? Insert graph xy plot. Let's just make sure we do get a bell curve. Plot z and P of z right there. Okay? That's your bell curve. You can see it's pretty much dead by what? Straight lines. Let's make that 10 grid lines. After about 3 sigma, right? So how do I get the area under the curve from z equals negative 1 to z equals plus 1? What would I do? I just integrate. So I would go to my calculus toolbar right here. If you don't see it, you go to view toolbars, okay? And you can pick up your calculus toolbar from there. And there's your calculus toolbar. Oops. Here. So integral from z equals negative 1 to z equals positive 1. Oops. You don't have to write plus. And then integral of p of z dz equals 0.683. What does that mean? From that area under the curve, remember the total area under the curve should be 1, right? In fact, if I did my area, I make that area very small, -5 to +5, that's essentially 1. Okay, you can see at 5 and -5 and 5, the function is pretty much dead. There's no more area. The area there is going to be negligible. So from -1 to 1, the area under the curve is 68% of the total area, 0.683. What that means is there is a 68.3% chance, okay, that your measurement is going to be within 1 standard deviation. Okay, remember when we had z equals 1 here, we had 1 standard deviation higher than the average, and -1 means 1 standard deviation below the average. So that's 68.7%, that's 68.3% chance. That's about roughly 2/3. So there's a 2/3 chance that if you did the measurement again, that it's going to fall within that interval. You are within 1 standard deviation. Okay, so that's the interpretation. And that should be the area you got when you did a previous exercise on Excel, where you integrated your Gaussian function, your normalized Gaussian function. What if I want to go from -2 to +2? (95.4). Okay, and in fact, you did get that when you did the integration before in Excel, right? And what's the likelihood that you're gonna? What's the probability of finding it within -3 and +3 within 3 standard deviations? 0.997. Okay. Now, if you go back to that Excel spreadsheet that I asked you to do, the probability, the t factors that I asked you to do. Okay. When you have a large t factor right here, let's just copy this one right here. What was it? T inverse 1 minus 0.997, and then let's say 49 degrees of freedom. You can see it's 3.1, right? If I make that number bigger and bigger and bigger, let's make that 100, it's going to approach 3. So let's make that 200. You can see this t factor approaches 3. Okay, so this confidence factor t approaches the value that you would expect, okay, if you were doing an infinite number of trials. Okay, so what about 0.954? What do you think the limit for that would be as n gets very large? This is going to approach 2. Okay, so if I do this, I copy this, it's 2. Okay, if I make that smaller, like 10, you can see it's not quite 2. But as I make that number bigger and bigger and bigger, 200, that's going to be 2. Okay, 0.683. If I copy that down here, you can see that's 60. Within 1 standard deviation, you have a 68% chance of being within 1 standard deviation. So that's the interpretation of standard deviation. Once within 1 standard deviation, 68.3% chance. Within 2 standard deviations, there's a 95.4% chance. And within 3 standard deviations, that's pretty much close to 100%, 99.7% confidence. Okay? So from -2 sigma to +2 sigma, what's the answer? 95.4%, right? And the interpretation is your random errors will be less than 2 sigma. Okay? 95% of the time. Within 3 sigma, within 3 standard deviations, this is 99.7%. Okay, so the rest of these, just explore on your own and answer the questions, finish up the rest of that. Let's move on to activity 4, propagation of errors. Okay. So the other questions there, just follow-up questions, had to do with interpreting standard deviation of the mean. So let's take a look at propagation of errors. The uncertainty of a measurement expresses standard deviation or the mean of the mean or confidence interval of the mean is often referred to as the random error. Okay. When a measured value is used in a calculation, we need to determine the impact of its random error on the calculated result. So in general, if you have f, you calculate it from a, b, c, and so on. And there are uncertainties in a, b, and c. So let's call that delta a, delta b, delta c. Okay, those uncertainties can be expressed as standard deviation or standard deviation of the mean or confidence interval. You just have to be consistent. Okay, then the uncertainty in the result, in the calculated result, okay, the square of the uncertainty in the calculated result is equal to the square of the partial derivative of f with respect to a times delta a squared plus the partial derivative of f with respect to b squared times delta b squared plus partial derivative of f with respect to c squared times delta c squared and so on. Okay, so this is the effect of uncertainty in A on the result. This is the effect of the uncertainty of B in the result. This one right here is the effect of the uncertainty of C in the result, and so on. So let's try that for a few of these things. Let's say you want to calculate the area, and you have your length is 3 plus or minus 0.10, and your width is 4 plus or minus 0.20. How do I get delta A? Well, first of all, what's my area going to be? 3.00 centimeters times the width, which is 4.00 centimeters. And that gives me how much? 12 centimeters squared. The question is, how should I report that? What should be the uncertainty in the 12? How do we do that? Well, delta A equals partial derivative of f of A with respect to, what does A depend on? Length and width, right? So partial derivative with respect to length times delta L squared plus partial derivative of A with respect to the width times delta W squared. Okay? So what happens there? What's the partial derivative of A with respect to L? This is like saying y equals x times a constant. You're taking partial derivative with respect to L. It's like taking a derivative with respect to L. Treat everything else as constant. So what would it be? It's just whatever the constant is, right? So this is just W. So that's W squared times delta L squared. Plus, what's the partial derivative of A with respect to W? A equals LW. If I were to treat L as constant, what's the derivative with respect to W? It's just L. So this is going to be L squared delta W squared. So that's your delta A squared. Okay? So how do I get delta A? It's the square root of W squared delta L squared plus L squared delta W squared. Okay. You might be wondering, this isn't quite the formula you were taught in your earlier courses, right? What formula did you learn when you're multiplying delta A over A square root of, when you're just multiplying, delta L over L squared plus delta W over W squared? Remember this from quantitative analysis or physics? You did this in physics too, right? Yeah. Well, you can actually show that this follows from this. How? What should we do? Let's go back to our expression for delta A squared. Let's divide both of these by A squared. So what would this be? Divide by A squared, which is length squared W squared, right? And this is length squared W squared. So what happens? W squared cancels, L squared cancels, and you have the formula that you learned from your earlier courses. Okay? So this formula I gave you is a more generic formula. And that's useful if now these formulas you learned in earlier courses are useful if the only thing you're doing is multiplying, right, or dividing, or if you're only adding or subtracting. What happens if you're just adding and subtracting? Like m equals m2 minus m1. Let's try that one. First of all, let's finish up that problem. Okay, A equals length times width, right? So 3.00 centimeters times 4.00 centimeters is 12 centimeters squared. So what should we do now? We're going to say delta A squared. Delta A is what? Square root of W times delta L squared. W squared delta L squared plus L squared delta W squared. And what would that be? Square root of, what's our W? 4 squared. And delta L is 0.1. And what's our L squared? 3. And what's our delta W? 0.2. So what would that be? Oops. It's going to be square root of 4 squared times 0.1 squared plus 3 squared times 0.2 squared. Is that 0.2 or 0.02? 0.2. So it's 0.72. Okay. So if that's 0.72, so this is 0.72. So it's 0.7. It's just an uncertainty, so I'll just keep it at 0.7. This is 0.7 square centimeters. So how should I report my area? Area should be 12.0 plus or minus 0.7 centimeters squared. Okay? That's what you have to do. So what I'd like for you to do is derive the uncertainties for this. In general, you'll find that well, actually, I'll leave it up to you to derive. Okay? So you should be able to do it on your own. And I'll check. We can talk about it next time. So work on that. And this is your post-lab report for this activity.